In this section, we will discuss the distribution function for electrons, F, which we know at t equals 0 should give us fully filled states when the states have energy less than the Fermi energy, and completely empty states when their energy is greater than the Fermi energy. For temperatures greater than 0, the distribution function will allow us to understand how electrons move from lower energy states to higher energy states when they acquire thermal energy. Consider first the equilibrium of classical particles obeying Boltzmann statistics, where the particles are confined to particular energy states. For example, the chemical reaction of two species of different energies E1 and E2 that interact and turn into two other species with energies E3 and E4. For a system in equilibrium, the forward reaction rate must be equal to the reverse reaction rate. The reaction rate depends on the number density of reactants or probability of finding a particle in the reactant state. For a reaction of two species, the forward reaction depends on the probability of finding particle in each of the reactant species at the same time, which leads to the product of the probability of finding the particle in each of the individual states. For the forward reaction to be equal to the reverse reaction, we then have the probability of finding the state in E1 times the probability of finding the state in E2 equals the probability of finding the state in E3 times the probability of state in E4. The Boltzmann probability distribution function from classical mechanics satisfies this requirement because the product of this exponential is the exponential of the total energy, and by conservation of energy, the total energy before the reaction should be the total energy after the reaction.
The classical Boltzmann probability function depends exponentially on energy, where particles with very high energy are much less probable than particles with lower energy. Classical thermodynamics tells us that the energy in the exponential scales with kT, or the thermal energy. In this way, particles at higher temperature are more likely to have higher energy. Boltzmann statistics results in the Arrhenius equation that we see in other areas of chemistry and physics. For example, the ratio of the population of two states is the exponential of the energy difference divided by kT. Now suppose that instead of classical particles, we have electrons that are in thermal equilibrium. Electrons must obey the Pauli exclusion principle such that no two electrons can occupy the same quantum state. This means that the forward reaction can only occur if there's space available in the product states. This means that the forward reaction rate depends not only on the probability of finding the particles in the reactant states, but also the probability of finding space in the product states E3 and E4, where the probability of finding space is 1 minus the probability of finding that state full. This leads to a thermodynamic equilibrium condition very different to what we found classically. The distribution function that fits these requirements for electrons or all fermions is known as the Fermi-Dirac probability distribution function. This distribution function satisfies our reaction condition for fermions as long as we continue to have conservation of total energy. This Fermi function gives us population characteristics that we were hoping for. For electron states with energies below the Fermi level, the probability of finding the state full is close to 1, whereas for electron states with energies above the Fermi level, the probability of finding them full is close to 0. There are a number of characteristics of the Fermi function that will help us understand how it works. For example, if we plug in the Fermi level EF for the energy, we get exponential of 0, which is 1, which results in f of EF equaling 1/2. So all of the curves, regardless of temperature, go through a half when the energy of the electron state is equal to the Fermi level. At 0 temperature, the Fermi function is such that we take the exponential of -infinity when E is less than the Fermi energy, making the exponential part 0 such that the Fermi function is simply 1, which is what we expect at energies less than the Fermi energy. When the energy of the state is greater than the Fermi energy at t equals 0, this exponential becomes infinity such that the Fermi function becomes 0. Again, as we expect above the Fermi energy. Thus, at 0 temperature, we get a step function giving us entirely filled states for states with less than the Fermi energy, and then entirely empty states for states with energy above the Fermi energy. For temperatures above 0, there's a transition region which gets broader as the temperature is increased. The width of this transition region scales roughly with kT. For states with high energy, well above the Fermi level, we have a distribution function which looks very similar to the Boltzmann distribution function for classical particles. For large energy, this exponential is very large, allowing us to ignore the added 1, and then flipping this upside down gives us a minus energy. The distribution of empty states for energies well below the Fermi level can also be thought of as a Boltzmann distribution. Mathematically, the probability of empty states is 1 minus f, and then the energy that goes in the exponential is the magnitude of the energy below the Fermi level.